Hello and welcome. Have you ever just stood outside on a perfectly clear night far away from the city lights and just looked up? There's a special kind of somnolence that happens then. The noises of the day, the cars, the notifications, the chatter, they all just fade away. And in that stillness you're left alone with the universe. Thousands of tiny shimmering points of light scattered across an ocean of perfect black. It's a strange feeling, isn't it? On one hand, you feel impossibly small. You're just one person on a small blue planet orbiting an average star in a quiet neighborhood of a galaxy that contains over 200 billion other stars. And that galaxy is just one of billions, perhaps trillions of other galaxies. It's enough to make your head spin. It's a smallness that can feel a bit lonely. But there's another feeling too, a feeling of connection. You realize that the same fundamental laws that keep your feet planted firmly on the ground are the same laws that are spinning those distant galaxies and igniting those faraway stars. You're not just an observer looking at the universe. You are the universe. You're a part of the grand cosmic story. You're a way for the cosmos to become aware of itself. Tonight I want to invite you on a journey. You don't need a spaceship, you don't need a telescope, all you need is your imagination. Let's set aside the worries of our daily lives for just a little while, the deadlines, the errands, the noise. Let's allow our minds to drift upward, past the clouds, past the moon, and into that deep, beautiful darkness. Let's travel together from the familiar glow of our own sun to the darkest, most terrifying and most magnificent objects in creation. Let's journey from the familiar night sky to the very edge of reality. When we look up at those stars, they seem so permanent. They seem like tiny, unchanging diamonds pinned to the sky. But they are not. The sky is not a static painting. It is a dynamic, violent and beautiful jungle. Those stars are not quiet dots of light. They are alive. Let's start with a star we know well, our sun. It is not a solid object. It is not a thing in the way a rock is a thing. It is a process. It is a colossal raging furnace. It is a sphere of superheated gas, a plasma so massive that its own gravity tries to crush it flat. Think of it as a constant, desperate battle. The star's enemy is its own immense weight. Gravity. Trillions upon trillions of tons of gas all being pulled inward toward the center. Gravity is relentless. It wants to collapse the star into a single tiny point. So why doesn't it? What is fighting back? The answer lies in the star's heart. In its core, the pressure and temperature are almost unimaginable. We are talking millions of degrees. It is so hot and so compressed that the very atoms of the universe are torn apart. In this inferno, the star has a secret weapon, nuclear fusion. A star is quite literally a giant non-stop nuclear reactor. It takes the most common element in the universe, hydrogen, and smashes it together. The pressure is so great that 4 hydrogen atoms are forced to fuse to join, becoming one new atom of helium. But here is the magic trick. This is the secret of the stars. If you were to weigh those 4 hydrogen atoms and then weigh the one helium atom, the helium atom would weigh just a tiny, tiny bit less. That missing mass doesn't just disappear. It is converted perfectly into a burst of pure energy, light, heat. This is the energy that pushes outward from the core. This is the star's defense. Every single second, our sun converts about 600 million tons of hydrogen into 56 million tons of helium. Those missing 4 million tons of matter are transformed into the energy that we call sunlight. That is the energy that hits your face on a warm day. That is the energy that powers all life on Earth. A star is not a peaceful object, it is a war zone. It is a perfect violent balancing act. The outward push of fusion energy is perfectly matched by the inward pull of gravity. This balance is what we call life for a star. It can hold this balance shining steadily for billions of years. But like any fire, a star needs fuel. That hydrogen in its core is not infinite. It's a fuel tank, and eventually that tank runs dry. For a star like our sun, this process takes a very long time, about 10 billion years in total. But for the true giants of the galaxy stars that are 10, 20 or even 50 times more massive than our sun, they are the rock stars of the cosmos burning through their fuel in just a few million years. What happens when the core runs out of hydrogen? What happens when the furnace stutters and the fire in the center dies down? The balance is broken. The outward push of fusion energy stops. But gravity never stops. Gravity never sleeps. It has been pulling inward patiently for the star's entire life. And now, there is nothing pushing back. The star begins to lose its fight, and gravity wins. Now for an average star like our sun, the end is relatively gentle. It will puff up into a red giant, its outer layers drifting away, and then the core will cool and fade into a beautiful glowing ember called a white dwarf. A quiet, dignified death. But we are not talking about quiet deaths tonight. We are talking about the Titans. When a truly massive star runs out of fuel, gravity doesn't just win, it conquers. The star's core, which is already incredibly dense, collapses. It doesn't happen slowly. It happens in less than a second. An object larger than the Earth can collapse down to the size of a city. The outer layers of the star, suddenly finding nothing holding them up, come crashing down onto this super dense core at a huge fraction of the speed of light. They hit this core and bounce back in the most powerful explosion the universe ever creates, a supernova. For a few weeks, this single exploding star can outshine its entire home galaxy of billions of other stars. It is an explosion of unimaginable power. But what about the core, the part that collapsed? This is where things get strange. This is where our understanding of reality begins to bend and break. For the most massive stars, the core keeps collapsing. The gravity is so immense that it overwhelms everything. It crushes the atoms themselves. Electrons are smashed into protons, creating a solid ball of neutrons. It becomes a substance so dense that a single spoonful would weigh as much as a mountain. But for the true giants, even that is not enough to stop the collapse. There is no force in there, not magnetism, not the nuclear forces, nothing that can halt the inward fall. The core, which might still have the mass of 3 or 4 of our suns, continues to get smaller and smaller and smaller. It collapses past the size of a mountain, past the size of a sugar cube. It collapses forever. It's crushed down to a point of zero size and infinite density. A single impossible point called a singularity. The star is gone, and in its place a monster is born. A place where gravity has become so powerful that it has warped and torn a hole in the very fabric of space and time. A region where the escape velocity, the speed you need to go to get away, is faster than the speed of light itself. And since nothing can travel faster than light, nothing can escape. Not a spaceship, not even a planet, not even light itself. If you shine a flashlight on it, the light falls in and never comes out. It is a one-way trip. It is the end of physics as we know it. This is the birth of a stellar mass black hole. So what does happen when you go into a black hole? The journey is a one-way street, and it begins at a place that doesn't really exist. It's not a wall made of brick. It's not a flaming barrier. It is a quiet, invisible mathematical boundary. We call it the event horizon. This is perhaps the most misunderstood concept about a black hole. We think of it as the surface. It isn't. The event horizon is simply the point of no return. To understand it, you have to understand escape velocity. Here on Earth, if you want to leave the planet, you have to travel very fast. A rocket must reach about 11 kilometers per second, that's over 25,000 miles per hour, to escape Earth's gravity. If it goes any slower, it will eventually fall back down. Every object with mass has an escape velocity. The Moon has one, Mars has one, the Sun has one. The more massive and dense the object, the higher the escape velocity. Now imagine an object so massive and so dense that its escape velocity gets higher and higher. Imagine you are in a spaceship backing away from this object. As you get closer, your engines have to work harder to pull away. You eventually reach a very special, very precise distance from the center of this object. At this exact distance, the escape velocity becomes 300,000 kilometers per second. That number is special. It is the speed of light. And according to Albert Einstein and every experiment we have ever run, nothing in the universe can travel faster than the speed of light. This is the event horizon. It is the line where the escape velocity equals the speed of light. If you are outside this line, you can still escape. It would be difficult, you would need powerful rockets, but you could turn around and go home. We can still see you. If you turn on a flashlight, we can see your light. But if you cross that line, even by 1 inch, you can never come back. The light from your flashlight can't come back, your radio signals can't come back, you can't turn your ship around and punch it. To leave, you would need to travel faster than light, and that is impossible. You are now quite literally in a land of no escape. This is why black holes are black. The light inside them is trapped just like you are. What would you feel? This is where it gets strange. The feeling depends entirely on the size of the black hole. If you are falling into a small black hole, one that is maybe only a few times the mass of our sun, your death would be quick and violent. Even before you reach the event horizon, you would be destroyed. The gravity of the black hole is so extreme that the pull on your feet, which are closer to the black hole, would be millions of times stronger than the pull on your head. This tidal force would stretch you. It would pull you apart, atom from atom. This process has a terrifyingly descriptive name, spaghettification. You would be stretched into a long, thin stream of plasma before you even reach the boundary. But if you fell into a supermassive black hole, like the one at the center of our galaxy, Sagittarius A star, which is 4 million times the mass of our Sun, the experience would be very different. Because this black hole is so enormous, the event horizon is very, very far from the center. The curve of gravity is much gentler. The tidal forces at the horizon are weak. You could cross the event horizon in your spaceship and you wouldn't even notice. You could look out your window, you could check your instruments, nothing would seem wrong, no alarm bells would ring, but you would be mathematically doomed. Inside the event horizon, space and time do something bizarre. They swap roles. Outside, you can move in any direction in space, up, down, left, right, but you can only move in one direction in time, forward into the future. Inside the event horizon, this flips. You can still move around a little, but the direction of time itself now points only one way toward the center. The future is no longer tomorrow. The future is the center of the black hole. Space-time itself is flowing into the center faster than the speed of light. You are trapped in the current. You cannot swim against it. You can only fall. So you have crossed the horizon. You are trapped. You are falling. Where are you falling to? The honest answer, the one that defines the very limit of our knowledge, is we do not know what is at the center. Our best current theory. Albert Einstein's general theory of relativity gives us an answer, but it's an answer that physicists hate. The theory tells us that all the matter in the black hole, all the mass of the original star, and everything that has ever fallen into it is crushed down to a single central point. A point of zero volume, a point of infinite density, a point of infinite gravity. It gives this point a name. It calls it the singularity. This is not a concept our minds can easily grasp. How can you have all the mass of a star in zero space? It's a paradox. For a physicist, the words infinity and zero volume are not answers. They are red flags. They are error messages. They are the universe's way of telling us that our theories are broken. Einstein's theory of relativity is brilliant. It describes the universe of the large. It describes gravity as the bending of space and time. It perfectly predicts how planets orbit stars, how light bends around galaxies, and how the event horizon of a black hole traps light. But when Einstein's theory tries to describe the center of the black hole, the equations fail. They divide by zero. They give us infinity. The theory breaks down. The laws of physics as we know them stop at the singularity. So what is really there? Is it truly an infinitely small, infinitely dense point, or is it something else? A fuzzball of vibrating energy strings, a ring instead of a point, a place where matter is destroyed, or a place where it is recycled and shot out into another universe. We don't know. Our science, our mathematics, our very understanding of reality stops dead at that central point. It is the ultimate mystery. It is the place where our knowledge ends. Why don't we know? Why do our best theories fail us in this one specific place? It's because the singularity is a battleground. It is the one place in the entire universe where the two great pillars of modern physics meet and go to war. Pillar number one is general relativity. This is Einstein's theory. This is the theory of the very big. It describes gravity. It describes space-time as a smooth-flowing fabric like a sheet of rubber. It explains how planets and stars bend this fabric. It works perfectly for things that are large and heavy. Pillar number two is quantum mechanics. This is the theory of the very small. It describes atoms, electrons, photons, and the strange fuzzy rules of the subatomic world. It explains chemistry, radiation, and the computers we are using right now. It works perfectly for things that are tiny and light. For all of human history, these two theories have lived in separate houses. Relativity handles the large-scale cosmos. Quantum mechanics handles the tiny microscopic world. But at the center of a black hole, these two worlds collide. The singularity is incredibly heavy. It has the mass of a star or more, so general relativity says, that's my territory. But the singularity is also incredibly small. It is crushed down to a subatomic size, or even zero, so quantum mechanics says, no, that's my territory. And the two theories give completely different answers. Relativity says space-time is smooth and can be crushed to infinity. Quantum mechanics says the universe is quantized. It comes in tiny individual packets. It says you can never crush something to zero size. There is a fundamental limit. The theories clash, they contradict each other. This is the crisis at the heart of physics. To understand the singularity, we need a new theory. We need a single theory that can do both jobs. We need a theory that can unite the world of the very big gravity with the world of the very small quantum particles. This is the holy grail of modern physics. It has a name, quantum gravity. We are not there yet. We don't have this theory. This is the great unfinished work of science. Scientists are trying. Some are working on ideas called string theory. which suggests everything is made of tiny vibrating strings of energy. Others are working on loop quantum gravity, which suggests that space-time itself is made of tiny unbreakable loops. These are just ideas. We haven't proven them. We haven't solved the puzzle. The center of a black hole is not just a place. It is a question. It is an invitation. It is the universe pointing its finger at a gap in our knowledge and challenging us. What happens at the center we don't know, but that I don't know is the most exciting phrase in science. It is the frontier. It is the dark, unknown territory where all the new discoveries are waiting. It is the problem that is waiting for the next Einstein, for the next generation of thinkers to finally solve. In our cosmic journey, we have encountered black holes born from the death of giant stars. These stellar mass black holes are impressive, certainly packing the mass of several suns into a point of infinite density. But the universe in its grand and often terrifying imagination has created something on a scale that dwarfs these objects entirely. These are the true giants, the gravitational titans of the cosmos, supermassive black holes. These are not just bigger, they are a different class of object altogether. We are not talking about 10 times the mass of our sun or even 100. We are talking about black holes that weigh millions, or in some cases billions of times the mass of our sun. Unlike their smaller stellar cousins, these giants are not found wandering the lonely suburbs of space. They are found in one specific place, the absolute dead center of almost every large galaxy, including our own Milky Way. They are the gravitational anchors of these vast cosmic cities. Every star, every gas cloud, every planet in a galaxy is participating in a slow grand orbit around this single central point of overwhelming gravity. This is not a distant theory. We have proof. Right in our own galactic backyard, about 26,000 light-years away in the direction of the constellation Sagittarius lies an object called Sagittarius A star. For decades, astronomers have watched stars at the very center of our galaxy, whipping around an invisible point at breathtaking speeds thousands of kilometers per second. To make stars move that fast, the object they are orbiting must be incredibly massive and incredibly small. The only thing that fits the description is a supermassive black hole. Our galaxy's central giant is relatively modest, weighing in at about 4 million solar masses. Its event horizon, the point of no return, would be large enough to swallow the orbit of the planet Mercury. But this is just a local example. When we look out at other larger galaxies, the scales become truly mind-boggling. The galaxy Messier, or M87, which became famous as the subject of the very first picture ever taken of a black hole's shadow, hosts a monster. That black hole weighs 6.5 billion times the mass of our sun. Its event horizon is not the size of a planet's orbit, it is larger than our entire solar system. These objects are majestic, yes, but they also present one of the greatest mysteries in all of cosmology. The question is not just what they are, but how they got there. This is a profound chicken and egg problem. What came first, the galaxy or the supermassive black hole? When we use our most powerful telescopes to look deep into space, we are also looking back in time. And when we look back to the dawn of the universe into when the first galaxies were just forming, we see these supermassive black holes already in place. How did they get so big so fast? The universe is about 13.8 billion years old. Growing a black hole to 1 billion solar masses is not easy. It needs to eat a lot of matter. This process takes time, and in the early universe time was in short supply. One theory suggests they started small. The very first stars in the universe were giants, perhaps hundreds of times the mass of our sun. When they died, they could have left behind heavy stellar black holes, maybe 100 times the sun's mass. These seeds then began to merge and collide, and they feasted on the dense seas of gas in the early universe. Over hundreds of millions of years, they grew into the giants we see today. But many scientists believe the math for this doesn't quite work. It's like trying to build a skyscraper in just 1 week by laying one brick at a time. It seems too slow to explain the super giants we see in the super early universe. This has led to a more dramatic and exotic theory: direct collapse black holes. In the unique extreme conditions of the primordial cosmos, perhaps enormous spinning clouds of pure gas clouds weighing hundreds of thousands of times the mass of the sun didn't fragment to form stars at all. Perhaps the entire massive cloud became unstable and collapsed directly into a black hole. This would create a massive seed right from the start, giving it a huge head start in the race to become a supermassive giant. Understanding this mystery is critical because these black holes are not just passive objects. They are active engines that shape the very galaxies they live in. When a supermassive black hole feeds the process is anything but clean. As gas dust and shredded stars spiral into the black hole, they form a vast flat accretion disk. The friction in this disk heats the material to millions of degrees, causing it to blaze with a light so intense it can outshine all 100 billion stars in its own host galaxy combined. We call these feeding, blazing black holes quasars. This incredible output of energy, this cosmic blowtorch, blasts outward, pushing on the gas in the rest of the galaxy. This feedback can be so powerful that it blows away the raw material for star formation, effectively shutting down the galaxy's ability to create new stars. It seems to be a cosmic balancing act. The galaxy feeds the black hole grows and becomes a quasar. The quasar's energy then stops the galaxy from forming more stars and thus cuts off the black hole's own food supply. The entire evolution of a galaxy from a bustling star-filled city to a quiet, retired galaxy seems to be regulated by the giant sleeping in its heart. Dark matter. The invisible scaffolding. As we pull our view back from the violent centers of galaxies, another, even stranger mystery comes into focus. It is a mystery defined not by a blazing light, but by a profound and total absence of it. It is the story of the other side of the universe, the invisible scaffolding that holds it all together. This story begins with a simple observation that led to a revolutionary crisis. In the 1970s, the astronomer Vera Rubin was doing a meticulous study of spiral galaxies like our own Milky Way. She was measuring how fast the stars in these galaxies were moving. In any spinning system like our solar system, we expect things on the outside to move slower than things on the inside. Mercury, close to the Sun's gravity, speeds along. Distant Neptune plods along slowly. Gravity gets weaker with distance. Everyone expected to see the same thing in galaxies. Stars near the bright center should move quickly, and stars on the dim outer edges should move much, much slower. Vera Rubin found the exact opposite. She discovered that the stars on the very outer edges of the galaxies were moving just as fast as the stars near the center. This observation was completely wrong. It defied the laws of physics as we knew them. This galaxy rotation curve problem was a catastrophe. A galaxy spinning this way should fly apart. The stars on the edges were moving at escape velocity. They should have been flung off into the darkness of intergalactic space like water spinning off a wet dog. But they weren't. The galaxies were perfectly still. There were only two possible explanations. Either our entire understanding of gravity laid out by Newton and Einstein was fundamentally wrong on the scale of galaxies, or there was more matter in the galaxy than we could see. A lot more. There had to be some vast invisible halo of stuff surrounding the entire galaxy. A massive sphere of material providing the extra gravitational glue needed to hold the fast-moving outer stars in their orbits. This mysterious unseen substance was given a simple name: dark matter. The name is precise. It is dark because it does not interact with light in any way. It does not shine, it does not reflect light, and it does not block light. It is completely, totally invisible to all of our telescopes, no matter what kind of light they use. It is matter because it has mass and therefore it has gravity. In fact, gravity is the only way we know it is there. The work of Vera Rubin was just the first clue. As we studied the universe more, we found evidence for dark matter everywhere. We see it in the way light from distant objects is bent as it passes through galaxy clusters, a process called gravitational lensing. The light is bent far more than the visible matter can account for. We see its imprint in the leftover heat from the Big Bang. When scientists added up all the numbers, the result was staggering. If you were to take the entire universe and put it in a pie chart, all the normal matter, every star, every galaxy, every planet, every cloud of gas, and every human being makes up less than 5% of the total stuff in the cosmos. About 27% of the universe is dark matter. The remaining 68% is an even more bizarre substance called dark energy, which governs the expansion of the universe itself. This means for every 1 pound of normal matter, there are more than 5 pounds of dark matter. This realization fundamentally changes our picture of the cosmos. A galaxy, it turns out, is not just the beautiful spiral of stars we see. The visible galaxy is just the tip of the iceberg, a small clump of luminous matter that has settled like sediment at the bottom of a vast, spherical, invisible halo of dark matter that is 10 times larger than the visible galaxy itself. Dark matter is the invisible scaffolding of the universe. It was dark matter that collapsed first in the early universe, forming a cosmic web of gravitational wells. Normal matter was then pulled into these dark matter wells, providing the seeds for the galaxies and stars we see today. We are in essence living in the leftovers. So what is it? This is arguably the single biggest unsolved question in all of physics. We know what it isn't. It can't be clouds of dust, they would block light. It can't be dead stars or planets, we would have seen their gravitational effects and there simply aren't enough of them. The leading hypothesis is that dark matter is a completely new type of subatomic particle. It would be a particle that is not part of our standard model of physics, which describes protons, electrons, and all other known particles. For decades, the most popular candidate for this particle was called a WIMP, which stands for a weakly interacting massive particle. The theory was that these particles are all around us all the time. Billions of them are likely streaming through your body every second, but because they are weakly interacting, they pass through normal matter, your body, the floor, the entire Earth as if it were a ghost. The only force they feel is gravity. How do you find a particle that is invisible and behaves like a ghost? Scientists are trying in several ways. The first is direct detection. They have built massive ultra-sensitive detectors deep underground in old gold mines to shield them from all other forms of cosmic radiation. These experiments, often using huge vats of purified liquid xenon, are essentially listening in the dark, waiting for the one in a trillion chance that a dark matter particle will fly through the entire planet and just happen to bump into the nucleus of one of their xenon atoms, causing a tiny detectable flash of light. After decades of listening, they have heard only silence. The second method is production. If we can't find dark matter in nature, maybe we can make it. This is a key goal of the Large Hadron Collider LHC in Europe. At the LHC, they smash normal particles' protons together at nearly the speed of light. The goal is to recreate the high-energy conditions of the Big Bang. They look at the debris from these collisions. If they smash two particles together and see all the new particles that fly out, but their calculations show that some energy or momentum is missing, that missing energy might have been carried away by an invisible dark matter particle that flew out of the detector unseen. So far, they have not found any conclusive evidence. The fact that we have not yet found a WIMP has forced scientists to become more creative. Perhaps dark matter is a different, much lighter particle called an action. Perhaps it's something even stranger. Or perhaps in a return to the original crisis, our theory of gravity is wrong after all. We are left in a curious and humbling position. We have mapped the invisible universe. We know where it is, how it shapes our galaxies, and how much of it exists. And yet its true nature remains a complete and total mystery. We ask the ultimate question, the one that sits at the very foundation of our existence. How can you get everything from nothing? We are told a story, the story of the Big Bang. We are told that in the beginning, all the matter and energy in the universe, every star, every galaxy, every planet, and every one of us was compressed into a point infinitely hot, infinitely dense, and smaller than a single atom. And then, bang! It exploded, and the universe was born. It is a powerful story, and it is for the most part true, but it has a problem. It feels incomplete. It feels like starting a movie 10 minutes in. It doesn't answer that core question, how can everything come from nothing? What caused the bang? What came before the bang? For a long time, science had no good answer. To ask what came before the Big Bang was considered nonsensical, like asking, what is north of the North Pole? The Big Bang, the theory went, was the beginning of time itself. There was no before. And yet that answer feels unsatisfying. It feels like a cheat. How can a state of infinite density just exist? And how can it create a universe like ours? A universe that is so incredibly large, so incredibly uniform, and so perfectly precisely of flat. This is where our story must evolve. We have learned that the Big Bang was probably not the absolute beginning. It was instead a moment of profound transition. It was the consequence of something else, something far grander, faster, and more violent than we ever dared to imagine. This idea is called inflation. To understand it, you must clear your mind of the dot. The Big Bang was not an explosion in space. It was the rapid unfolding of space itself. But inflation was the trigger. Imagine in this before time there was no matter. No light, no particles, not even empty space as we know it. There was just a pure, powerful energy field, an inflation field. This field had a massive amount of potential energy stored within it, like a boulder perched at the very top of an impost. Write for me in English. Don't rewrite the headings. The words are easy to understand. The scientific symbols are written in letters about 2,000 words. Part 4, the story of beginnings and endings, approx. 2 to 500 words. Before the Big Bang tone epic grand. Question, how can everything come from nothing? Explain that the Big Bang may not be the absolute beginning. Introduce the theory of inflation. an extremely early period even before the Big Bang when the universe expanded exponentially faster than light. The universe grew from smaller than an atom to larger than the entire observable universe in just a tiny fraction of a second. When inflation stopped its enormous energy poured into space creating matter and radiation, what we call the Big Bang. The future of the universe, tone, quiet, vast. Question, how will the universe end? Previously we thought gravity would slow the universe down, possibly collapsing it big crunch. The Nobel Prize-winning discovery. The universe is not just expanding, it is accelerating its expansion. A mysterious dark energy is pushing everything apart. The most likely outcome. The universe will continue to expand forever. Galaxies will drift apart, stars will die out. A cold, dark and silent future, heat, death, T. It was unstable. And then a tiny subatomic patch of this field began to roll. In a moment so small it is almost meaningless, a time of about 1/1,000,000th of a trillionth of a trillionth of a trillionth of a second, this energy was unleashed. But it didn't explode. It did something stranger. It pushed. It caused the fabric of space itself to expand at a rate that defies all logic. It expanded exponentially. It doubled in size and doubled again, hundreds of times, all in this infinitesimal sliver of time. This is not expansion like a bomb. This is expansion faster than the speed of light. Now, you may have been told nothing can go faster than light, and that is true for objects within space, but this was space itself, stretching. The rules are different. It was as if you had a ruler and the ruler itself was stretching, so the distance between the 1-inch mark and the 2-inch mark was suddenly a mile and then a light year. In this single violent instant, a region of space smaller than a proton, smaller than the nucleus of an atom, was stretched, until it was larger than our entire observable universe today. A single quantum ripple was magnified to the scale of a galaxy. It was an event of such total world-defining power, it took the universe, which was likely a messy, crumpled, chaotic quantum foam, and stretched it. It stretched it so vast, so fast, that it became perfectly mathematically flat, like pulling a crumpled piece of paper so hard and so fast from all sides that all the wrinkles are instantly smoothed out. This is why our universe looks flat. Inflation ironed it. It also explains why the universe looks the same in all directions, why the temperature of the background radiation from one side of the sky is almost identical to the other. They are separated by billions of light years. They should never have been able to talk to each other to even out their temperature. But with inflation, they were connected. They were neighbours side by side in that initial subatomic patch. They had evened out their temperature, and then inflation ripped them apart, flinging them to opposite ends of the cosmos. And then it stopped. As suddenly as it began, the inflation field settled. The boulder reached the bottom of the hill. That immense potential energy it held had to go somewhere. It was converted. It poured into the new vast flat space it had just created. That energy transformed into a superheated soup of particles and radiation. Matter, antimatter, light, all churning in a furnace of unimaginable temperature. This was the Big Bang. The Big Bang was not the creation from nothing. It was the after-party. It was the moment the energy from inflation became the universe we know. The bang was the starting gun for the universe we see, but inflation was the mechanism that built the racetrack, flattened it, and loaded the gun. So how can everything come from nothing? Perhaps it can't. Perhaps it came from a different kind of something. A state of pure energy with the potential to inflate, to transform, and to become the complex, beautiful, and vast cosmos we call home. From this furious, explosive birth, we now turn our gaze in the other direction. From the first moments of time we look forward to the very last. We have asked how it all began. Now we must ask the other darker question. How will the universe end? For most of history, this question was the domain of philosophy and religion. But in the 20th century, science finally had the tools to make a prediction. The story we thought was simple. It was a cosmic battle between two forces. In one corner, the momentum of the Big Bang, the initial push that sent all the galaxies flying apart from each other. In the other corner, the steady, persistent pull of gravity, the force of every galaxy, every star, every atom, pulling back on every other atom. The fate of the universe depended on who won. We saw two possible futures. If the push was strong enough and there wasn't enough stuff, enough gravity in the universe, that the expansion would just go on forever. Galaxies would fly apart, stars would burn out, and the universe would fade into a cold, dark, empty state. We called this the Big Freeze. But if there was enough stuff, if gravity was strong enough, it would eventually win. The expansion would slow down. It would stop. and then slowly at first, and then faster and faster it would reverse. Galaxies would stop moving away and start moving toward each other. The universe would fall back in on itself, collapsing into a fiery singularity, a mirror image of its birth. We called this the Big Crunch, a cycle of fire to fire. For decades, astronomers argued, which is it, do we freeze or do we burn? The only way to know was to measure it. We had to look at the most distant objects we could find and measure how fast the universe was expanding in the past compared to today. In the late 1990s, two teams of astronomers set out to do just that. They used distant exploding stars, supernovae, as standard candles to measure cosmic distances. They were looking for the slowdown. They were trying to find out how much gravity was breaking the universe. What they found changed everything. There was no slowdown. The brakes weren't working. In fact, it was the opposite. The universe was not slowing down. The expansion was speeding up. It was accelerating. This was a discovery so profound, so shocking, it won the Nobel Prize. It turned our entire understanding of cosmology upside down. Something else was in the driver's seat. Gravity wasn't winning. The momentum of the Big Bang wasn't winning. Some unknown, invisible, mysterious force was pushing the accelerator to the floor. We do not know what it is. It seems to be a property of space itself, a kind of anti-gravity, a repulsive force that is woven into the vacuum. We give this mystery a name because that is what scientists do. We call it dark energy, and it has sealed our fate. In the early universe, when everything was close together, gravity was king. It pulled matter together to form galaxies and stars. But as the universe expanded, space grew. The galaxies moved further apart and gravity's grip weakened. But this dark energy, it seems to be constant. Every new patch of space that opens up contains more of this energy. Today, the universe has expanded so much that dark energy has taken over. It now makes up more than 70% of everything in the cosmos. It is pushing and it is winning. So what does this mean for our future? It means the Big Crunch is not coming. The end will not be a fiery collapse. The end will be quiet. The most likely outcome is the one we once called the Big Freeze, but it is now far more profound. We call it the heat death. It is not a single event, but a slow, majestic and terrible fading into eternity. It will happen in stages. First, the age of isolation. For the next few billion years, things will look normal. Our own Milky Way galaxy will collide and merge with the Andromeda galaxy, forming one giant supergalaxy we can call Milkdromeda. But outside our new home, the accelerated expansion is doing its work. Other galaxies, the ones not bound to us by gravity, are being pushed away, faster and faster. In about 100 billion years, every galaxy outside our own local group will have accelerated away from us so fast that they will cross an event horizon. Their light will no longer be able to reach us. They will fade redshift and then vanish. Imagine a night sky. Our giant Milkdromeda galaxy will be a blaze of light, but beyond it nothing, not a single point of light. The entire rest of the universe will have been erased from our view. We will be an island alone in an endless, expanding, silent darkness. The universe becomes a lonely place, but time, of course, moves on. Next, the age of stars. Inside our lonely galaxy, stars will continue to be born alive and die for trillions of years. But the supply of interstellar gas is finite. Eventually all the gas will be used up, star formation will stop. One by one, the stars will burn out. The massive blue stars die first, then the yellow stars like our sun. The last to go will be the small dim red dwarf stars. They sip their fuel so slowly they can last for 10 trillion years, but even they will eventually sputter out, becoming cold dead embers. The universe will go dark. We enter the degenerate era. The cosmos is now a graveyard. It is filled only with the cold remnants of stars, black holes, neutron stars and cold white dwarfs. The planets are frozen rocks orbiting dead stars in a blackness deeper than we can imagine. And still time stretches on. The timescale is now so large that writing it as a number is almost pointless. A 1 followed by 37 zeros. Over these timescales, even the fundamental forces of nature get to work. Protons themselves, the very building blocks of atoms, may be unstable. Theory suggests that they will eventually decay, dissolving into a puff of light and other particles. One by one, the dead stars and frozen planets will simply evaporate, dissolve. The only things left will be the black holes. We enter the black hole era. For a time that makes the age of protons seem like a heartbeat, black holes will be the only organized matter in the universe. They will drift through the darkness, slowly swallowing any stray matter, growing larger. But even black holes are not forever. As Stephen Hawking discovered black holes evaporate, they leak a tiny, tiny amount of Hawking radiation. It is an impossibly slow process. A black hole the mass of our Sun will take a 1 followed by 67 years to evaporate. The supermassive black holes at the centers of galaxies will take a 1 followed by 100 years. A Google years. One by one, even these final cosmic monsters will hiss away shrinking until their last moment, when they explode in a final tiny and meaningless flash of light in the dark. And then nothing. We arrive at the final state of the universe, the heat death. The universe will be an unimaginably vast, cold, dark and empty place. It will be a thin uniform soup of scattered photons and fundamental particles separated by infinite distances, all at a temperature just fractions of a degree above absolute zero. There is no more hot or cold, there are no structures, there is no change. The arrow of time will have lost all meaning because nothing happens. Entropy has reached its maximum. The universe has reached its final stable resting state. It is the end of physics, the end of time, a cold, dark and silent eternity. This is the story of our cosmos, born in the fire of inflation a fraction of a second of unimaginable violence, and fated to die in the ice a slow, quiet and infinitely long fade into the dark. It is the grandest story ever told. From a beginning we can just barely glimpse, to an end we can barely dare to imagine. Let's take a step back to that idea of cosmic inflation, the explosive expansion that took our universe from a subatomic point to the size of a grapefruit in a fraction of a second. The standard picture is that this process happened, and then it stopped allowing the energy to cool form particles and eventually become the stars and galaxies we see today. But this leads to a fascinating and slightly terrifying question. What if the off switch was faulty? What if inflation didn't stop everywhere at the same time? This is the doorway to the eternal inflation hypothesis, one of the most mind-bending concepts in modern cosmology. Imagine the space that is inflating not as a single object but as a vast energetic ocean. This ocean is by its very nature expanding at a fantastic rate, constantly creating more of itself. Now imagine that in some places this expansion can slow down and stop. It's like a patch of this raging ocean suddenly becoming calm. In that calm patch, the inflationary energy converts into matter and radiation just as we discussed. A big bang happens. A bubble universe is born. The catch is the ocean around this new bubble universe never stopped inflating. It continues to expand, stretching the space between this new bubble and any others that might form. In this model, the Big Bang that created our universe wasn't a one-time event. It was just one bubble, forming in an infinite, eternally boiling pot. This is the multiverse in its grandest form. Not just other planets, but other realities. Infinitely far away from us, pulled away by the unstoppable expansion of the metaspace between us, other bubbles are constantly forming. New Big Bangs are happening right now. But what are these other universes like? Are they just copies of ours? The theory suggests probably not. In fact, they are likely to be unimaginably different and almost certainly sterile and hostile. This comes down to the constants of nature. In our universe, we have very specific rules. Gravity has a specific strength. The speed of light has a specific value. The force that holds atomic nuclei together, the strong nuclear force, has a precise strength. We have 3 dimensions of space and 1 of time. These settings seem perfectly fine-tuned to allow for complexity. If gravity were just a tiny bit stronger, the universe would have expanded after the Big Bang, only to collapse back on itself in a big crunch, before the first stars could even form. If gravity were a tiny bit weaker, it would never have been able to pull matter together to form stars and galaxies in the first place. If the strong nuclear force was slightly different, protons might not stick to neutrons, and the only element in the universe would be hydrogen. There would be no carbon, no oxygen, no water, no planets, and no life. In the eternal inflation model, each new bubble universe might be created with a different set of random values for these constants. As the bubble cools from the inflationary ocean, its fundamental physics freeze in place. Our universe won one of an infinite lottery. We landed on the settings that allow stars' chemistry and eventually us. Out there in the infinite foam of other bubbles are universes that died in their first second. There are universes that are just thin, cold gas clouds of hydrogen with no stars to light them. There are universes with 5 dimensions of space where the laws of gravity are completely different. There are universes where light doesn't travel at the speed it does here, or where the charge of an electron is different. These universes aren't parallel in the science fiction sense of a world just like ours, but where you wore a different shirt this morning. They are fundamentally different, built on the different physical laws, and almost all of them are failed universes dead on arrival. We live in the one that succeeded precisely because we are here to observe it. This idea, known as the anthropic principle, suggests that, of course, we find ourselves in a universe with perfect constants for life. If the constants were different, we wouldn't be here to ask the question. But the inflationary bubbles are not the only version of the multiverse. Another, perhaps even more exotic idea comes from the cutting edge of theoretical physics, specifically from string theory. This is the concept of brain theory. This theory starts by challenging our most basic assumption that we live in a three-dimensional universe. We experience 3 dimensions of space, length, width, height, and 1 of time. But what if that's just all we can see? Brain theory suggests that there may be many more spatial dimensions, perhaps 10 or 11 or even more, but that we are stuck in a 3-dimensional subspace. Imagine a single flat sheet of paper. To a 2-dimensional creature living on that sheet, their entire universe consists of forward, backward, and left-right. They would have no concept of up-down. They might deduce the existence of a 3rd dimension if, for example, a 3-dimensional object like a pencil passed through their paper world. They wouldn't see the pencil. They would only see a 2-dimensional circle, the cross-section of the pencil suddenly appear, perhaps change size, and then disappear. It would look like magic, a violation of their laws of physics. In brain theory, our entire universe, everything we can see, touch, and measure, including all the galaxies of the observable universe, exists on a 3-dimensional brain, short for membrane. This brain is our sheet of paper. Where is this brain? It is floating in a higher dimensional space, a vast unseen reality called the bulk. This immediately presents a new multiverse concept. What if there isn't just one brain? What if the bulk is filled with countless other brains, other universes, perhaps floating parallel to our own? They could be in this higher dimensional sense less than a millimeter away from us, yet we would be completely unaware of them. We are, with one possible exception, locked to our own brain. Our forces, our particles, and our light cannot leave our 3D sheet and travel into the 4D or 5D bulk. That one exception might be gravity. Some physicists theorize that gravity is the one force that is not stuck to the brain. It leaks between dimensions. This could explain why gravity is so incredibly weak compared to the other forces like electromagnetism. A tiny refrigerator magnet can defeat the entire gravitational pull of the Earth. Gravity's true strength might be diluted because it is spread out over all the extra dimensions. This brings us to a revolutionary new idea for the Big Bang. In the old model, the Big Bang was the start of everything, the beginning of time and space. In this brain world scenario, our Big Bang may not have been a beginning at all. It may have been just an event. Imagine 2 massive parallel brains, 2 separate universes floating in the bulk. Perhaps they are drawn to each other by the gravity leaking between them. They drift closer and closer, and then they collide. The energy of this collision would be catastrophic, unimaginable. That colossal release of energy injected into the brains at the point of impact would be hot, dense, and explosive. It would, from the perspective of a creature on one of the brains, look exactly like a Big Bang. The collision itself is the Big Bang. It sets our universe in motion, expanding and cooling, forming the structures we see today. In this model, the universe didn't come from nothing, came from the collision of something that already existed. And it suggests that this might not be the first time. Our universe could be part of an endless cycle of collisions, rebounds, and expansions, a cosmic rhythm, playing out in the unseen dimensions of the bulk. So we have these incredible hypothetical realities, the infinite bubble universes of eternal inflation and the stacked parallel worlds of brain theory. Can we go? Can we visit these other worlds, or forgetting them? Can we even hope to travel to the nearest star in a reasonable time? This leads us to the great unyielding barrier of physics, the speed of light. In science fiction, ships engage a hyperdrive or warp drive and jump across the galaxy. This is called faster than light or FTL travel. In reality, the universe seems to have a very strict rule number: you cannot. The speed of light in a vacuum, about 300,000 kilometers per second, is not just a high score. It is the fundamental speed limit of the cosmos. It is the speed at which all massless particles like photons, the particles of light, must travel. And it is a speed that anything with mass like a human or a spaceship can never reach. Why? The reason comes from Albert Einstein's special theory of relativity. As an object with mass accelerates and gets closer and closer to the speed of light, its own mass begins to increase. From the perspective of a stationary observer, the spaceship would get heavier and heavier and heavier. As it approached 99.999% of the speed of light, its mass would be approaching infinity. To push an object with infinite mass, you would need an infinite amount of energy. There is not enough energy in the entire observable universe to make a single atom reach the speed of light, let alone pass it. It is a physical concrete wall. But there is an even deeper, more fundamental reason why FTL travel is forbidden. It's not just an engineering problem, it's a logic problem. The speed of light isn't just a limit on travel, it is the limit of causality. Causality is the simple common sense law that a cause must always happen before its effect. You must light the match, cause before the fire starts effect. Painter must dip the brush, cause before the paint appears on the canvas effect. This is the logical one-way arrow of time that holds our entire reality together. Einstein showed that speed and time are deeply connected. The faster you move, the slower time passes for you relative to someone standing still. This is not a theory, it is a measured fact. But this relationship has a strange consequence. If you could break the light speed barrier, you wouldn't just be moving very fast. According to the mathematics, you would be reversing causality. If you could send a signal faster than light, you could, from certain reference points, send a signal that arrives before it was sent. You would see the effect before the cause. This opens the door to logical impossibilities known as paradoxes. The most famous is the grandfather paradox, though in this context we can call it the parent paradox. Imagine you build an FTL ship. You use it to travel back in time, which FTL effectively allows to the day before your parents first met. You then accidentally or intentionally do something to prevent them from ever meeting. What happens if they never meet, you are never conceived, you are never born? But if you are never born, then who was it that went back in time to stop them from meeting? This is a logical contradiction. It's a statement that is self-referentially false. The universe, it seems, hates logical contradictions. The laws of physics are built from the ground up to prevent them. The universal speed limit, the speed of light, is the universe's firewall. It is the causality protection agency. It ensures that time flows in one direction that causes precedent effects and that reality remains logical and coherent. So travel to other stars. It will be a slow boat, travel to other bubble universes or other brains. The barrier seems absolute. We are for all practical purposes locked inside our own patch of reality, governed by our own fundamental rules. This seems like a cosmic prison. The speed of light and the law of causality forbid us from traveling FTL and forbid us from changing the past. But what about the future? Can we travel in time? The answer is surprisingly and demonstrably yes. You are doing it right now. We are all moving forward in time at a steady rate of 1 second per second. But what if you want to get to the future faster? This is not science fiction. This is a direct consequence of Einstein's relativity. We already discussed that the faster you move through space, the slower you move through time. This is called time dilation. Let's do a thought experiment. Imagine two twins. One, the Earth twin, stays home. The other, the traveller twin, gets on a highly advanced spaceship. This ship is capable of accelerating to 99.99% of the speed of light. The traveller twin goes on a journey. She travels to a nearby star and comes back. According to her ship's clocks, the journey took her exactly, say, 5 years. She lands back on Earth 5 years older and gets out to meet her twin. She will not find her twin. She will find her twin's grandchildren or great-grandchildren. Because while only 5 years passed for her on the fast-moving ship on Earth, which was stationary relative to the ship, decades or even centuries have passed, from her perspective everything on the ship was normal. From the Earth twin's perspective, his sister's clock, his sister's heart rate, her very aging process, everything on that ship was happening in extreme slow motion. This is real. We prove it every single day. At particle accelerators like the Large Hadron Collider, LHC scientists accelerate subatomic particles called muons. A muon at rest has a very short, very specific lifespan. It decays, falls apart into about 2.2 microseconds, millionths of a second. But when those muons are accelerated in the LHC to 9.99% of the speed of light, their time dilates. Their internal clocks slow down dramatically. From our perspective in the lab, their lifespans are stretched by a factor of 30, 40 or 50. They survive far longer than they should. They are in effect time travelers. By moving at near light speed, they are leaping forward into their own future. So traveling to the future is simply an engineering problem. If we could build a ship that could sustain near light speeds, a massive engineering problem, as it would require unimaginable energy, you could buy a ticket. You could travel for 1 year on that ship, and when you returned, you would land on Earth in the year 3225. You would have effectively and irreversibly traveled 1,000 years into the future. But what about the other direction? Can we travel to the past? Based on everything we know, the answer is the same as the FTL question no. The door to the past appears to be firmly and fundamentally shut. The reason is the exact same one that forbids FTL travel causality. If you could travel to the past, you could create a paradox. You could break the chain of cause and effect. You could prevent your own birth. The universe's logic would unravel. The laws of physics, as we understand them, are a one-way street. Time, like an arrow, flies from the known past into the unknown future. You can slow down your personal journey into that future by moving very fast, or by sitting near a very strong gravitational field like a black hole, another form of time dilation. By doing so, you can let the rest of the universe speed ahead of you, allowing you to jump into their future. But you can never turn the arrow around. You cannot revisit the past any more than you can unscramble an egg, or put the shattered pieces of a glass back together perfectly just by rewinding a video. The past is fixed. It is the record of what has happened, the chain of causes that led to the present effect, which is you. To break that chain is to break reality itself. The cosmos may be filled with wonders, other universes, other dimensions, and a future we can in theory leap forward to see. But it is also a place of rules. And the most important rule, the one that holds the entire structure of space and time together, is that you can't see the movie before the script is written. The past is history and the door is locked. And so we stand at the edge of this cosmic ocean looking out at the endless scattering of lights, and we have to ask the question, the biggest question of all. With all this vastness, all of this scale, all of these potential homes, is there anyone else out there? Are we alone? For most of human history, this question was pure philosophy. It was a matter for priests and storytellers. But today it is a scientific testable question, and the data we are getting back is staggering. Based on the data from missions like the Kepler Space Telescope, our best estimates suggest there are around 20 billion planets just like Earth right here in our own Milky Way galaxy. Let's be very clear about what that means. That is not just 20 billion planets. That is 20 billion rocky planets roughly the same size as ours, orbiting in the habitable zone of their star. That's the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on the surface. 20 billion. That number is so large that it almost breaks our intuition. It implies that if you look up at any random handful of stars in the night sky, you're probably looking at a star that has a planet where you could stand where water could flow. The ingredients are there. This calculation has turned the question from, is there life out there, to, why wouldn't there be life out there? If you have 20 billion chances, 20 billion laboratories all running the same experiment with the same ingredients, water, carbon, energy, it seems statistically inevitable that something would arise. So how do we find it? We can't go there, not yet. They are too far. We look for their shadow, we look for their breath. When one of these distant planets, an exoplanet, passes in front of its parent star, the star's light dims just a tiny, tiny fraction. But more than that, some of that starlight filters through the planet's atmosphere if it has one. That light then travels for hundreds or thousands of years until it reaches our telescopes like the James Webb Space Telescope. We can catch that light and spread it out into a spectrum like a rainbow. And in that rainbow there are black bars missing pieces. Those bars are the chemical fingerprints of the gases in that planet's air. We are quite literally analysing the atmosphere of worlds light years away. What are we looking for? We're looking for biosignatures, signs of life. We look for oxygen. Oxygen is incredibly reactive. It doesn't want to stay free in an atmosphere. It wants to bind with rocks and minerals. If you find an atmosphere filled with free oxygen like Earth's is, it means something is actively constantly replenishing it. On Earth, that something is photosynthesis. We are looking for the signal of a billion alien forests. We look for methane. Methane can be made by volcanoes, but it's also made by life, specifically by microbes that digest and release it. And the real sucking gun, finding oxygen and methane in the same atmosphere. These two gases should destroy each other in a chemical reaction. Finding both at the same time suggests the planet is in a state of chemical disequilibrium. It suggests that two different biological processes are pumping both gases into the air simultaneously. We are even looking for technosignatures. This is a more unsettling idea. We can look for gases that nature never makes. Things like chlorofluorocarbons or CFCs. These are industrial pollutants. If we find CFCs in the atmosphere of a distant planet, it wouldn't just mean we found life. It would mean we found an active and perhaps careless industrial civilization. The search is on, but we don't even have to look that far. We have fascinating candidates right here in our own solar system. We look at Mars. Today it's a cold, dry, irradiated desert, but we know from our rovers that billions of years ago it was a different world. It had rivers, lakes, and possibly a shallow northern ocean. It had all the same ingredients Earth did at the exact same time. It had a head start. Life on Earth started very quickly, almost as soon as the planet cooled. So did life also start on Mars. And if it did, where did it go when the planet died? The surface is hostile, but just a few feet underground, it's possible. It's possible that deep in the Martian soil, protected from radiation, there are still dormant or even active microbial bacteria. A kind of shadow biosphere waiting to be discovered. And then there is Europa, one of Jupiter's large moons. From the outside, it's a billiard ball of solid ice frozen in the deep cold of the outer solar system, but inside it's alive. The immense gravity of Jupiter is constantly squeezing and stretching Europa. This tidal friction generates heat, and that heat is enough to melt the ice from the bottom up. Beneath that frozen crust, miles thick, we are almost certain there is a global liquid water ocean. This ocean has been liquid for billions of years. It may contain more liquid water than all the oceans of Earth combined, and at the bottom of that ocean, just like on Earth, we expect there to be hydrothermal vents gushing heat and chemical nutrients from the moon's core. On Earth, those vents are teeming with life. They are oases that do not need the sun. They are a complete ecosystem built on chemical energy. Could the same be true on Europa? In that dark, silent, deep ocean, could there be an entirely different branch of life completely alien to us? So the galaxy seems packed with potential homes. Life seems to start easily, maybe even in our own backyard. Which leads to the great terrifying silence. If the galaxy has 20 billion Earths, and if life is common, and if the galaxy is 13 billion years old, where is everybody? This is the Fermi paradox. The physicist Enrico Fermi asked it simply. The numbers say the sky should be full of civilizations, but we see nothing. We hear nothing. There is only silence. Our civilization has only had radio technology for about 100 years. Our solar system is 4.5 billion years old. The galaxy is much older. If another civilization had gotten just a tiny head start, say 100,000 years, which is nothing in cosmic time, they should be everywhere. They should have had ample time to colonize the entire galaxy, or at least send signals so powerful they would be unmistakable. And yet, nothing. This silence suggests something. It suggests that one of our assumptions is wrong. Maybe travel is impossible. Maybe everyone is hiding, or maybe the part we think is easy is actually the hard part. Maybe simple life, bacteria, algae, simple microbes is everywhere. Maybe the universe is full of slimy, single-celled worlds, but maybe complex, intelligent life is impossibly rare. Look at our own planet. This is the only data point we have, but it's a chilling one. Life appeared on Earth almost 4 billion years ago, almost as soon as the planet was habitable. It was fast. But for the next 3 billion years, nothing happened. Think about that. For 3/4 of all life's history on Earth, the most complex thing on the planet was a mat of green algae. The planet was covered in a film of simple single-celled organisms. They were born, they ate, they died, for 3 billion years. And then in a geological instant, something incredible happened. A revolution. An event that, as far as we know, happened exactly one time on this planet. It was not a competition, it was a merger. We had two basic types of simple cells floating around, bacteria and archaea. They were both simple but fundamentally different. And one day, one of them, an archaea, tried to consume a bacterium, but it failed to digest it. Instead, in a 1 in a trillion accident, the bacterium survived inside its predator, and it began to work for it. That trapped bacterium became a specialist. It stopped worrying about fending for itself and focused on one thing: energy. It became what we now call the mitochondrion, the power plant that exists inside every single one of your cells. This new combined cell was the first eukaryote, and it changed everything. This merger gave the new cell thousands of times more energy than its simple competitors. It was like suddenly upgrading from a single AA battery to an entire nuclear power plant. With this new vast surplus of energy, this cell could afford to build new things. It could build a nucleus complex structures. It could specialize. And most importantly, it could afford to team up with other cells to build a body. Every single thing you've ever seen that is not a microbe, every tree, every insect, every fish, every bird, every human, all of it is a eukaryote. We are all the descendants of that one impossible accidental merger. It took nearly 4 billion years for that one event to happen. Maybe that is the great filter. Maybe the universe is filled with 20 billion worlds of bacteria, all waiting for an accident that will never come. But even winning that biological lottery wasn't enough. To get from that first complex cell to a civilization that can look back at the stars, you need one more thing. Time. You need billions of years of stability. Evolution is slow. It needs a long, quiet, stable runway to build complex creatures. You cannot have the planet constantly being boiled or frozen or blasted by radiation. You need a safe harbor. And it turns out Earth is an extraordinarily safe harbor thanks to a series of cosmic accidents. First, there is our moon. Our moon is not normal. It is enormous compared to our planet. No other rocky planet in our solar system has anything like it. It's so big Earth and the moon are almost a binary planet system. And we know how it got here, a catastrophic collision. Early in Earth's history, a rogue planet about the size of Mars slammed into the young Earth. The impact was so violent it nearly destroyed our world, blasting a huge portion of the planet's mantle into orbit. That ring of debris over millions of years coalesced into our moon. It was a violent birth, but without it we wouldn't be here. The moon's primary job, its most important contribution to life, is stability. Its massive gravitational pull acts like an anchor. It holds Earth's axis of rotation steady. Our planet is tilted at 23.5 degrees, which gives us our predictable seasons. Without the moon, that tilt would be chaotic. It would wobble violently like a dying top. Our axis might swing from 0 degrees no seasons to 90 degrees where the poles point directly at the sun. Imagine the climate on a world like that. Imagine a place where every few million years the North Pole suddenly becomes the equator and the equator becomes a frozen ice cap. The surface would be alternately sterilized by extreme heat and extreme cold. Complex land-based life would be impossible. Our moon keeps our seasons mild and our climate relatively stable, and it has done so for the billions of years that evolution needed to do its work. Second, there is our guardian, our bouncer, the planet Jupiter. The current theory of our solar system's formation is called the Grand Tack hypothesis. It's a beautiful, chaotic story. The theory goes that Jupiter formed first in the outer solar system, but it didn't stay there. Its gravity caused it to spiral inward toward the Sun. It moved all the way in to about where Mars is today, and its massive gravity acted like a snowplow, scattering or absorbing all the rocky material in the inner solar system. This is probably why there are no super-Earth's planets bigger than Earth but smaller than Neptune in our system, even though they are the most common type of planet in the galaxy. Jupiter cleared out the region. But then Saturn formed, and as Saturn also began to drift inward, the two gas giants fell into a perfect gravitational resonance lock. This lock stopped Jupiter's inward march and began to pull both of them back out away from the Sun to where they reside today. This tack, like a sailboat changing direction, did two things for us. First, by clearing out the inner solar system, it allowed the four small rocky planets Mercury, Venus, Earth and Mars to form from the scraps that were left without being bullied or absorbed by larger planets. Second, by moving back out, Jupiter now stands guard in the outer solar system. It is our cosmic vacuum cleaner. Its immense gravity acts as a shield deflecting or absorbing the most dangerous high-velocity comets and asteroids that come flying in from deep space. It protects us from the very impacts that would have reset evolution, that would have broken the blackboard, just as life was getting interesting. When you put it all together, the picture becomes almost overwhelming. We are not just lucky. We are the product of an impossible biological accident, the eukaryote merger that happened only once. We are protected by a giant moon that was born from a planetary catastrophe which stabilizes our world. And we are shielded by a gas giant that tacked at just the right time, clearing our orbit and protecting us from impacts. Any one of these things is unlikely, for all of them to happen in one place. It leads you to a profound and perhaps lonely conclusion. The universe may be full of stars and planets, but it may be empty of us, empty of complex conscious thinking beings. It changes how you see the sky. It's not a collection of destinations. It is a reminder of why our home matters. We are not the center of the universe, but we might be the most precious thing in it. We are the cosmos made aware. We are the part of the universe that has woken up through an absurdly improbable chain of events and is now able to look back out and appreciate it. And it means that this pale blue dot, this one fragile, stable, lucky world, is not just our home. It may be the only home, and it is utterly irreplaceably rare. We are connected to the universe in the most intimate way possible. It is not just something out there that we look at. We are the universe. Every piece of you, every atom in your body was forged in the heart of a star that exploded billions of years ago. The carbon that forms your cells, the oxygen you are breathing right now, the iron in your blood, the calcium in your bones, all of it was created in a stellar furnace scattered across space and then gathered together over eons to eventually form this planet and to form you. We are quite literally stardust. Our brains are a part of this physical universe. They are made of ordinary matter, the same stuff as a planet or a cloud of gas. Our brains must follow all the laws of physics like gravity and electromagnetism. And yet something absolutely magical happens. This collection of physical material, this 3-pound organ sitting inside our skulls, is able to do something that, as far as we know, a rock or a star cannot. It is able to be aware. This is the great paradox. We are physical matter, but we are also experience. The universe through us has woken up. It has developed a way to look at itself, to think about itself, and to wonder where it came from. This self-awareness, which we call consciousness, remains one of the greatest mysteries we have ever faced. It is as deep and as challenging as the mystery of dark matter, the invisible substance that we know holds our entire galaxy together. It is as strange as a singularity, that impossible point at the center of a black hole where all the laws of physics seem to break down. We do not know how a collection of cells following simple physical rules can create the rich inner world you experience right so, and the feeling of understanding these words, the memory of your childhood, the emotion of love, or the simple appreciation of a beautiful colour. We are the universe's way of knowing itself, and we are still a mystery to ourselves. So how do we even begin to understand this vast cosmos we are part of? We are small and the universe is almost infinitely large. The key we discovered is that the universe does not operate on chaos. It operates on rules. There is a deep underlying order to everything. The way a planet moves around its sun, the way light travels through space, the way a tiny snowflake forms, it all follows a precise and beautiful pattern. We discovered the language that describes these patterns. It is not a spoken language, it is the language of mathematics. Mathematics is the instruction manual for reality. It is a language that needs no translation. An equation describing gravity works the same on Earth as it does in a galaxy 1 billion light years away. It allows us to see the fundamental harmony of the cosmos. The most incredible, most awe-inspiring thing about this language is its power to predict. It allows us to see parts of the universe that we have not yet found. It lets us write the story before we have read the end. There is a perfect example of this. In the 1960s, scientists were working with just pen, paper, and the language of mathematics. Their equations told them that for the universe to make sense for matter, to have mass at all, there must be an invisible field permeating all of space. And this field must have a specific particle associated with it. They described this particle in detail purely from their mathematical theories. They called it the Higgs boson. It was just an idea. For decades, it was only a ghost in an equation. Then, 50 years later, humanity came together to build the largest, most complex machine in the history of the world, the Large Hadron Collider. It is a massive ring miles and miles across, buried deep underground. Its job is to smash tiny particles together at almost the speed of light to recreate the conditions just moments after the universe was born. And in 2012, after all that time, all that effort, and all that genius, they found it. They found the particle. It was really there exactly as the mathematics had predicted half a century before. We had used the language of nature to see a fundamental piece of reality long before our tools were strong enough to prove it. So what does this all mean? Where does it leave us, these tiny, self-aware beings on a small blue planet orbiting an ordinary star in a quiet corner of one galaxy among billions? It is easy to look up at the endless darkness and feel small, to feel insignificant. But we should feel the opposite. In all of our searching of the skies and all our listening for signals, we have found only silence. No one else is broadcasting. We see no signs of other great civilizations. Of course, the universe is vast and we have only just begun to look. But it's entirely possible that at this moment in time in our entire Milky Way galaxy, we are the only ones. We might be the only civilization that has woken up. We might be the only minds capable of looking at the stars and feeling wonder. If that is true, it does not make us small. It makes us infinitely precious. It means that all the beauty of the cosmos, the brilliant colours of a nebula, the graceful rings of Saturn, the fiery dance of distant galaxies only has meaning because we are here to see it. We are the observers. We are the meaning makers. Without a mind to appreciate it, the universe is just a collection of atoms. We provide the awareness. And what is the engine that has driven us to learn all of this? What force pushed us from our first moments of awareness to building the great machines that find new worlds? It is one simple, beautiful, and powerful human trait: curiosity. It is the urge to know what is over the next hill. It is the drive that built ships to cross the ocean and then built ships like the Apollo rockets to cross the emptiness of space and leave footprints on our moon. It is the same curiosity that makes us build the Large Hadron Collider to ask, what are we made of? Science in its purest and most noble form is just organized curiosity. It is our deep, fundamental need to understand, and now it is time to rest. As you prepare for sleep, think about that night sky. When you look up, you're not just looking out, you're also looking back in time, and you are looking at your own origins. Every star is a sun, every star is a story. Every one of them is a possibility, a place that future generations might one day know. We carry that entire universe inside our minds. It is time to let that curious mind rest and to carry these quiet wonders into your dreams. The cosmos has been turning for billions of years and it will be waiting for us when we wake. Good night.